Hello, welcome to session 12 in the series Analog Circuit Design using ADS. My name is Anurag Nigam, and in the last session, session 11, I talked about high frequency response of a common source amplifier. Now I'm going to cover the high frequency response of a common gate amplifier, right? So let's get started. So this is going to be a I somehow want to write it with high frequency response of common gate amplifier. Okay, so let me first draw the diagram of a common gate amplifier with all the capacitors. So there is an input node which is a small signal ground. The gate is a small signal ground, and then there is a CGD3 which is to ground, right, from this node. So this can be considered in an output capacitance, right? Yeah, so that will be in considered there. Okay, so now here the signal is applied to the source. The signal is applied to the source, let's say with the input resistance RS. Okay, and this is Vin, and then you have got Vi, and there is a current I in, right? And this, of course, the voltage Vi appears across here, so GM is inverted, so I can write this as GM3 plus GMB3, right? And because Vi is the same as for GM3 and GMB3, Vi is the same input, so that's there. Then we have got this resistor which is GDS3, and then now depending on how you connect the depending on how you connect the body terminal, the CGD3, okay, so no, not CGD3, depending how you connect the body terminal, the what do you call CDB would become either the part of the load to the ground or a part of this capacitance to the source. So if basically the device sits in the well, then CDB would come in would be accounted in this capacitor, right? So let's have this capacitor as C1, and then we have another capacitor which is C2, and I will list to you what is that. And then there is this G2, and then there is this VO. So this is the drain terminal, right? The drain terminal. This is the gate terminal, and this is the source, right? And this is to ground. Now I'm assuming that the body terminal is connected to the ground rather than to the source, but we will see how much difference does it make later on. Okay, so now come on. Okay, so now let's try to see what I have over here. Okay, so I have C2, which will be equal to CDB2. Okay, so mind you, this is 1, this is 2, this is 3. So CDB2 is for this transistor, and this is CDB3. Okay, CDB2 plus CDB3 plus CGD3 plus CL. Now CGD3 is connected to ground because I'm consuming body is connected to ground. Otherwise this CGD3 will come into C1, right? So now okay, Okay, and that would be the only capacitance in C1, right? Because other than that, everything is accounted in C2. So for now, let us assume that CGD3 has been accounted into C2. So all I have is now this, right? Okay, so the input capacitance is going to be CGS plus CSB, right? The input capacitance will be, sorry, C in would be equal to CGS3 plus CSB3, right? Okay, and then G2 has got G2 basically has got GDS2 plus GL, which is the load. So this is G2. Okay, so now having said that, let's write the equation at the output node. So at the output node, we have VO multiplied by all the connected conductances, GDS3 plus G2, correct? GDS3 plus G2 plus SC2, okay, minus the adjoining node is VI times of GDS3, and as the current is flowing in instead of out, I have VI times of GM3 plus GMB3 should be equal to 0. Now collecting the terms, I have VO by VI is equal to GM3 plus GMB3 plus GDS3 divided by GDS3 plus G2 plus SC2, right? Okay, now what about the input voltage? So for input voltage, I have got this equation. I'll write here. Okay, for input voltage, the equation is at this node. So I'm not assuming that I'm going RS into picture. I'm going to assume that IN is flowing in, right? So what's going to happen is I am going to have VI into the conductance connected to this GDS3 minus VO, the conductance in between is GDS3, minus, or in this case it will be the current flowing just one second, the current flowing out of the node, which is going to be GM3 plus GMB3 times of VI. Okay, GM3 plus GMB3 times of VI, right? Okay, and then minus IN, the current, so this is going to be plus, and IN is going to be minus because this is the current flowing in, equal to 0. Now I'm going to collect the terms of VI, which will be GM3 plus GMB3 plus GDS3, right, minus VO. Now VO is again this same term here, GM3 plus GMB3 plus GDS3, right, divided by GDS3 plus G2 plus SC2 times of VI times of GDS3. Okay, so times of GDS3 times of VI. Okay, so this is there. Now the other side is going to be, okay, so this is there, and is going to be equal to IN. Okay, so let me just simplify these terms. VI common is GM3 plus GMB3 plus GDS3, and this will be 1 minus GDS3 divided by GDS3 G2 plus SC2 times of Vi is equal to In. So Yin is In by Vin, or In by Vi, which will be equal to 1 divided by, just 1 second, 1 divided by, okay, so here Yin by In by Vi, right? So In by Vi will be GM3 plus GMB3, sorry, MB3 plus GDS3, that is the common thing on the left hand side, and this would be GDS3 subtracted, so G2 plus SC2 will remain, right? So you will have GDS3 divide G2 SC2 divided by that, right? So this will become 1 and this will be that. So this term would simplify to 1 plus GDS3 divided by G2 plus SC2. So this will be equal to Yin, and then the total input would be Yi, which will be Yin plus of SC in, right? And that would be equal to that. So now I have Vi by Vin is equal to GS by GS plus Y in, right? GS plus Y in, or Yi, yeah. So AV would be equal to VO by Vi, so VO by Vin. So I'll multiply the two terms, right? So I would have, so if I assume Rs equal to 0, so that means GS is infinity. So this would be dividing by GS, so this term will become 1, right? So then the exact, okay, in case there is no load, GL is also 0, right? So is there a G2? Okay, G2 will be GDS2 only, right? Okay, so it will be GM3 plus GMB3 plus GDS3 divided by okay, so in this case this factor will become 1, then AV will be equal to VO by Vn, which would be VO by Vi only, GDS3 plus G2 plus SC2, GDS3 plus G2 plus SC2. Now if I assume that GL is equal to 0 because RL equal to infinity, no loading at the output, then G2 would become RDS2 only, or GDS2 only. So in that case AV will be equal to GM3 plus GMB3 plus GDS3 divided by GDS2 plus GDS3, common I will take out, and I'll be left with 1 plus SC2 divided by GDS2 plus GDS3, right? Now this one what you have over here is AV0. AV0 divided by 1 plus S over GDS2 plus GDS3 divided by C2. Right. So now this equation, if you see that there is only one pole. There are no two poles here. There is only one pole here. And that pole WP1 is equal to minus of GDS2 plus GDS3 divided by C2. So that's very simple, right? There is only one pole here. And okay, so that's the story. And there would be a pole because of the input node, but this would be the dominant, but it will be far away. So I can assume that there is only one pole which will cause a phase roll off of 90 degrees, and then beyond certain very high frequency, then the input node, there will be one more pole, right? But primarily, if I assume, I can only see one pole in the voltage gain of a common gate, and that should reflect the response. So let's see the response of a common gate. So if I see the response of a common gate over here, you will see that the phase has rolled by 90 degree only, right? Okay, so you can see that this 90 degrees over here, this line, right? So basically you had only one rollover. There is no question of a zero, there is no question of a second pole. Right? There is no question of a second pole, there is no question of a zero. Only roll off is 90 degrees. Right? So you understood that this is very much simplified if I take a common gate. Now you will see that there are two curves here. One is the dark blue, other is the light blue. And this is the phase roll off. And the gain roll off also has got two magenta and red. Okay, so what I'm trying to do here is, one of the response is with the body connection to the ground, other response is the body connection to the source, right? So does it introduce something, body connection to the source? Well, it will introduce a zero, right? It will introduce a zero. So let's see what that would be, right? So in that case, let's look at the mathematical treatment. In that mathematical treatment, I would take this one, this small signal, and then I'll just copy this, okay, over here. Okay, now in this I would introduce C1. This is CGD1. Okay, so now let's see what happens. Okay, so now C2 would be equal to C. Okay, so CGD is over here, right? Sorry about this. The CGD is over here, so let me draw it dotted. Okay, anyways, one terminal is grounded, then this CGD3 is accounted in C2. Okay, so C2 will be equal to CGD3 plus CL. Okay, and now because of this connected to the source, body terminal connected to the source, now C1 will be equal to CDB2. Let me see if CDB2 will come in here, because CDB body terminal for the the second transistor, which is this one. Okay, so the body terminal CDB, and this is small signal ground, so there will be CDB2, sorry, here, and this will be only CDB3. Right? So now what has changed here? Anything changed here in terms of treatment? Yes. So let's write this equation again. VO by VO times of what is connected to that, right? VO times of GDS3 plus SC1 plus C2, right, plus G2. Okay, and then minus of SC2, minus of GDS3 plus SC1 times of VI, right? Okay, and then the current flowing in is negative, GM3 plus GMB3 times of VI should be equal to 0. So then we have VO over VI is equal to GDS3 plus GDS3 plus G2, right, plus SC1 C2. Just 1 second. Let me see if I'm recording. Okay. Okay, little mistake here. So let's just solve this. Okay, so it will be VO by VI. So it will be GM3 plus GMB3 plus GDS3 plus SC1 divided by G2 plus GDS3 plus SC1 plus C2. That's correct. And YI would be equal to, okay, so YI would be equal to GM3 plus GMB3 plus GDS3 plus SC1 divided by 1 plus GDS3, and SC1 is additional here, divided by G2 plus G2 plus SC2, right, and GL I'm assuming 0. Okay, so GL I'm assuming to be 0, right? So now I have, this is YI plus it will be SC in. So C in this case is going to be CSB plus the same thing, right? And then okay, so now I would have AV. So this term GS by GS plus YI would be tending to 1 because GS is infinity. So I will be left with AV will be approximately equal to GM3 times of, so if you remember, it was GM3 over here, right? Over here AV0 was GM3 plus GMB3 plus GDS3, right? So over here GM3 plus GMB3 plus GDS3 plus SC1, SC1. Okay, so that will be there divided by G2 plus that thing. So I'm going to assume that G2 is just GDS2, right? So I have GDS2 plus GDS3, right? GDS2 plus GDS3 common, and then this is 1 plus S divided by GDS, okay, S divided by GDS2 plus GDS3. So nothing changes, but instead of just C, there will be C1 plus C2. Okay, so what has happened now? If I was to assume that GM is much larger than this term, right? So I have GM common out. I have 1 plus S over GM3 divided by C1, correct? Divided by GDS2 plus GDS3 times of 1 plus S divided by GDS2 plus GDS3 divided by C1 plus C2. Okay, so now what has happened here? AV has become AV0 times of 1 plus S by omega Z divided by 1 plus S by omega P1. So now you see that omega P1 is equal to minus of this number, right? GDS2 plus GDS3 divided by C1 plus C2. So nothing has changed in case of a in case I have done a body connection to the source. Okay, so CDB3 has come along with GDS3, right? But that has introduced a 0 in the left hand side, which is going to be minus GM3 by C1, correct? Okay, so now where does this reflect? Where does this left hand side 0 reflect? So if you see the response, here, what you see over here, okay, sorry, okay, what you see over here is it's trying to correct, right? It's trying to correct the phase. So that's a very minor 0 which is introduced, right? Sorry. Okay, so that's a minor 0 which is introduced here. That's why a kink in the phase. Okay, so what we have learned from this? We have learned from this that if you have a common gate, you have a pole which is because of just a single pole you have. So you have a roll off of 90. And then there would be a second pole very far away because of the input node C in, right? And that C in is going to be very far away because the Miller is not referred to the input, but the Miller is grounded. The CGD3 is grounded rather than it is being referred to the input side. So what has happened is that the second pole is still there, but it is very far away because C in is just CGS3 plus CSB3. So I can write that, okay, CSB3 plus CGS3. Okay, this will cause the second pole, right? This will cause the second pole. So the resistor associated with that would be Rin. And if Rin is 0 or very small, so that is going to happen. So this is going to be omega P2. Now minus. So now if so the Miller is not there. So Miller is not there because the gate terminal is grounded. So CGD3 has gone to ground, right? So it is not referred to the input node. Now what is to the input node is only CSB3 plus CGS3, and then there is a Rin, okay, or RS, what I called RS, and I'm assuming RS to be 0. So this pole has gone to infinity. So that is why in this you do not see a second pole coming in, or even if it comes, it will be far away. Okay, so that makes the common gate to be very stable. So I'm going to stop here for a high frequency response of a common gate. Okay, thanks a lot.